All right. We go now chapter 3 and 4. We're going to start chapter 5. We're going to go over these 8 topics. And then we're going to go in detail about instructional objectives. I'm going to start with chapter 5, with the states of matter. Can you guys see my slide page for 3 states of matter?
Yes, sir.
Okay. Let me summarize the 3 states of matter. First, we're going to look at solids on the left corner, and then the liquid, and then the gaseous state. You can see solid state has regular order in the solid. Water molecules are stacked nicely. Liquid state is disorderly, but both of them are water is an example here. Water molecules are close to each other in both states. Therefore, solid state and liquid state is called condensed states of matter. Condensed. That means they are close to each other. But there are differences between solids and liquids. On the other hand, gaseous state is a lot of space between the particles, making the matter, in this case, steam. There's no intermolecular forces. The highest intermolecular forces in solid state, lowest intermolecular forces in liquid solid. There's no intermolecular force in gaseous state. A solid has a definite volume. So does liquid state. Liquid state takes up the volume of the shape of the container, takes up the volume of the container. Solid state has its own, like ice cube, water in a glass, take up the shape of the glass. The gas has no definite shape. Its shape is shape of the container. Solid maintains its own shape. Liquids takes the shape of the container. Gases don't have definite volume. It takes up the space of the container. Solid particles lie close together in a regular pattern. In a crystalline solid, you have regularly ordered water molecules. In liquid state, water particles are close but move past each other. Therefore, they can roll over. Therefore, liquid have flow properties. Liquid can flow from one place to another. Gaseous state is different. Its particles are far apart and they randomly move in space. So let's look at some problems. Excuse me. Which matter has the weakest attractive forces between molecules? We already talked about gaseous state as the weakest attractive force. Let's look at the choices. A solid has weakest attractive forces between its molecules. That's not the answer. Liquid has the weakest. Liquid has attractive intermolecular forces. They are not weak. Gas has the weakest. That's what the correct answer is. The attractive forces between the molecules are the same. It's not true. The changes of state take place because of the attractive forces. See the correct answer for this question. Weakest attractive forces are in gases. Which of the following leads to increase in kinetic energy of molecule? This is kind of a jumping into kinetic molecular theory. According to that, kinetic energy is energy of moving particles. It's calculated one half mass times velocity squared. Kinetic energy. Kinetic energy increases with temperature. As the temperature of a substance increases, particles start to move faster. Then temperature is the main thing that is increasing the kinetic energy. Surface area is not. Density is not increasing. Density is dependent on the amount of substance, its molecular weight, molar mass. Increase in intermolecular attractive forces. Kinetic energy decreases as intermolecular attractive forces operate on particles of the sample of gas or liquids or solid. Therefore, this is not the correct answer. Therefore, only correct answer is B. Kinetic energy increases with the temperature. Let's look at the next question. Which of the physical states represented by the model given here? This is condensed space. This is not a gas. It looked like a solid or liquid, but solid has more orderly arrangement. Liquid has disorderly. If you look at these particles in here, they are kind of not orderly arranged. Therefore, this should be a representation of a liquid. That's the B is the correct answer. We go to next question. Which substance change when the substance change from A to B? Which of the following statements is true? Let's look at the change. That's a gas. This is B is a liquid or solid? How many of you see as a solid? The previous diagram, we talked about liquid. This is regular rearrangement of solid particles. When velocity of the molecule increase, that's not true. When gas goes to a solid, velocity, they are held in fixed places. Velocity decrease. Strength of the intermolecular forces increase. That the kinetic energy that's true. Let's look at that. The strength of intermolecular forces increase and the kinetic energy of that's also true. I cannot see that changing this is covered here. The strength of intermolecular forces increase and the kinetic energy of the molecule decrease. This is more correct. First two are correct, but D includes both. Therefore, most correct answer is D. The temperature of a substance is increased to a very low value temperature. Let's see which of the models represent this substance at the lowest temperature. Which one has the lowest temperature? This is liquid. Solid has the lowest temperature. Therefore, B is the correct answer. All right, we looked at some of the properties of three states of matter. Now we're going to go into details of gaseous state. Gaseous states show pressure. So there's a barometer made by Evangelista Torricelli, Italian scientist. What he measured was gaseous pressure. This instrument he used is called barometer, mercury, made out of mercury. What he did was he filled up a mercury tube with mercury. I cannot draw. He filled the mercury tube and keep this close and put that in the mercury in the container below. Both contain mercury. When he put this down, mercury drops. But if you push this tube into the mercury, if I push tube here, that the space on the top called vacuum, there's nothing in there. It disappears. This level of mercury is 760 millimeter mercury. When he saw that, he's the first one to create the vacuum. He noticed this column, which is 760 millimeter mercury, is always close to that value in the atmosphere. If you have a globe, if you have this barometer placed in the close to sea level at any location, the atmospheric pressure is 760 millimeter mercury. This is also called 760 millimeter mercury is called tau. So this discovery allows us to measure atmospheric pressure. This 760 tau or millimeter mercury is called one atmospheric pressure. Atmospheric pressure is almost close to this 760 millimeter mercury, but it changes depending on the day. Why this is always 760 is atmospheric pressure depends on the pressure exerted by the gases in the whole atmosphere. From top of the atmosphere to the sea level, mercury column with this much of mercury, 760, this whole air from sea level to the top of the atmosphere weighs 760 millimeter mercury column, therefore atmospheric. If you go higher in the elevation, atmospheric pressure going to get reduced. So this behavior is based on air acting as a liquid. Normally, when you go underwater, pressure increases. Somehow he got the idea how to measure the pressure of the atmosphere based on Torricelli barometer. Do you guys have any questions about how he measured atmospheric pressure? Now, knowing atmospheric pressure is one atmospheric pressure is 760 millimeter mercury. There are other units we've been using. 762 is same as millimeter mercury, is same as to millimeter mercury. There's another unit called Pascal. That's about 100,000 Pascal, 1 atmosphere. Rounded off, it's about 100,000. 1 atmospheric pressure, mercury column 760 is same as 29.92 just in mercury. We also use a pressure unit called bar. It's about 1 atmosphere, 1.01, close to 1 atmosphere. Bar is almost close to 1 atmosphere. The gas tanks, when you get a gas tank, helium tank, that gauges measure pressure in per square inch, pressure in pounds per square inch. That's about 15. 1 atmosphere is about 15 psi. So we can use different units to measure pressure. A manometer is a device which we use to measure pressure. Barometer is the Torricellian. The barometer we talked in the previous slide. Okay. A manometer is a device with mercury attached to a gaseous sample to measure pressure. Device that measure pressure is called manometer. Here the mercury level is not equal. Therefore, gaseous sample has 80 millimeter mercury pressure. Now we don't use mercury for measuring pressure. What you use is, there are material which are called piezoelectric crystals. When you apply a pressure onto the crystal creates a voltage which is proportional to the pressure applied. Therefore, most of the devices measuring pressure use piezoelectric crystals. Therefore, in our vehicles, ignition temperatures, in our application, pressure is measured by piezoelectric devices. Therefore, it's directly measured by the current produced by the pressure. Let's answer some of the questions about pressure. Which of the following instrument is used to measure atmospheric pressure? Altimeter is on a plane. Altitude is measured by altimeter. A barometer is the one Torricelli used for measuring atmospheric pressure. Manometer is general name for devices like piezoelectric devices that measure pressure of a gaseous sample. Thermometer is not used to measure pressure. Thermometer is temperature. So this is the correct answer is C. B, I'm sorry, barometer is the correct answer. What is the average pressure of the atmosphere at sea level? That's the one atmosphere exists. That's that number we got from on the sea level. That's the average. Answer is A. Which of the following is the SI units of pressure? SI unit is Pascal. It's 100,000. About 1 atmosphere is equal to 100,000 Pascal. D is the correct answer. Which of the following is true of in the mercury level on the same side? A J tube is the one that we saw the mercury J tube to measure the sample in gaseous sample in that previous slide. Both sides is the same, means pressure of the sample is equal to atmospheric pressure. C is the correct answer. If the J tube is attached to the mercury level is same, that means inside pressure is equal to outside pressure. Which of the following units can be used to measure air pressure? All of these. Which of the pressure relationship? This is about 15, close to about 15. That's not exactly 15. 1 atmosphere is equal to 15 pounds per square inch. This is correct. Tau is same as millimeter mercury. This number is different. It's not 15.8, it's 14.6956. This is wrong. This is wrong. Therefore, correct relationship is A. Now, you heard about blood pressure. You have systolic and diastolic. It depends on pressure of the blood. When the heart pumps, it increases the pressure. When blood is pumped into cardiovascular system, is the diastolic. It's about somewhere around 120 upward. Systolic means when heart is not pumping. So you know the systolic is around 80. Systolic is 120. what is the pressure in the units of ATM. Now the conversion factor is 760 millimeter mercury. So you start with this pressure given. Then this is the conversion factor. To cancel out, you get that number when you do the calculation, 128 divided by 760. Answer is C. That's how you do the pressure calculation using factor label method. A scuba diver take up a compressed gas air tank, which is at 2,350 psi pounds per square inch. What is the pressure in millimeter mercury? This is the conversion factor we already talked about previous slide. I gave several conversion factors. To convert PSI, you use. So you set up the equation. You start with this PSI and arrange the conversion factor so that PSI cancel out and leaves the answer in millimeter mercury. The answer is C. Another calculation. Tank is at same PSI. What is the unit in atmospheric unit? This is two units here. PSI and 760 millimeter mercury is same as 1 atmosphere. So conversion factor is given here. So you rearrange equation. That's the given pressure. This is the conversion factor given here. So you line up, do the calculation to get the ATM value. That's A. It's pretty simple how to convert. You will be given the conversion factors. You don't have to remember. So same PSI. Now they're asking in Pascal. So you start with PSI, this conversion factor, rearrange to a fraction. This divided by 1 PA. Idea is to cancel the PSI. Leave the ATM. When you use factor label method, you can figure out whether to multiply or divide to do the conversion. Answer is D. Now we're going to look into gaseous behavior of gases. We mainly look at gases, how when you look at gases, we are looking into how the volume of a gas changes with pressure, how the volume of a gas changes with temperature, how the pressure of the gas changes with temperature. The first behavior of gases is between volume and pressure. When you increase the pressure of a gas, volume decrease. That's the inverse relationship. When you increase the pressure, volume decrease. This relationship, volume is 1 over pressure, is called Boyle's law. Now, one thing you need to understand is when you're changing volume and pressure, you have to have temperature constant and the amount of gas, which is measured in moles, amount has to be constant. Otherwise, they will change if you change, you cannot change all of them. You have to hold one constant. Two of them, there is pressure, volume, temperature, and N. You can only look at these two. You have to hold temperature and amount of gas. That's the number of moles of gas constant. Normally, when you have a proportionality constant, proportionality sign, this proportionality in mathematics is replaced by a constant. That means PV is equal to a constant. When you have a constant, PV is equal to K. To remove the constant, you need P1, V1, and P2, V2. Then make them equal. So Boyle's relationship after removing the constant is P1, V1 equal to P2, V2. This equation is called mathematical form of Boyle's law. You will be given initial value of pressure of a gas, initial volume, and the final volume is given. What is the T value? You rearrange the equation. You can calculate the P2. Those calculations we're going to do in problems later. Charles' law is between temperature and volume. It's a directly proportionality. Volume increases as the temperature increases. Now, proportionality constant is now V over T. That's the constant. To remove constant, we have to get two readings, just like we did in the. So Charles' law is volume of a gas sample given, temperature is given. Very important to remember, temperature should be in Kelvin. Whatever the temperature value, it should be in Kelvin. If you are given Celsius, you have to convert to Kelvin. Gas laws behave based on Kelvin temperature. Therefore, we have to convert temperature to Kelvin. Gay-Lussac's law is same idea. Now the pressure is directly proportional to temperature. We're going to look into gauge select flow in few slides later. Which of the following laws relate the volume and the pressure of a gas when amount of and the temperature amount is moles kept constant? That's Boyle's law. Now we're going to look into amount of substance of a gas, how it changes with the volume. That's direct relationship. You get the similar equation, how the amount of a gas changes the volume of the gas. This is Boyle's law. Volume and pressure. N and T held constant. Amount is N. And temperature is held constant. Therefore, answer is B. At constant temperature, the pressure of 6.0 liters volume gas sample increased from pressure to this pressure, P1, that's P2, that's V1. New volume is the V2. P1, P2, V1 is good. What you do is you get the idea Boyle's law equation and solve for V, rearrange this equation. P1, V1 is divided by P2 is, these are the values I got from right here, right here, right here. Answer is 3 liters. D is the correct answer. At constant pressure, the temperature of a 3 liter V1, calculate the temperature if the volume change to V2. This is 56. Remember, this has to be converted to Kelvin. You add a 273. Let's do the calculation. You solve for the temperature is the question. T2. So we solve for T2. So you get the T2 value, which is B. At constant pressure, temperature of a volume is gas increases from T1 to T2. New volume of the gas. So you do the new volume and get the number of correct variables. You get 5.3. That's the D. Now these calculations are similar. V1. That's the same question, right? Let's see. A constant pressure, temperature, that's a charge law. Volume of a gas decrease from when the temperature decreases from new volume of the gas. This is increase. This is decrease. So that's a decrease. This is a increase, 5 points. Then it goes to 3 liters here. Answer is C. At constant pressure, temperature of a gaseous sample, V1, increase from calculate the new volume. Now you have to convert these temperatures to Kelvin and solve for V2, new volume. New volume is V2. That's the V1. So when you plug in these numbers, the temperature values in here, you get 4 points. That's the C. The Gay-Lussac law is the last law we talked about, pressure and Kelvin temperature. It's same as Charles' law. So equation is this. Now we can do calculation for pressure and temperature variables, but it's similar to Charles' law. We're not going to do that. There are 3 laws we came up with. Now, once you get these 3 laws, we can see we can create a combined gas law. This is one. When you combine all these gas laws into one equation, and you can use that combined gas law, knowing which of the two, which one is cell constant. Volume is cell constant. Then it becomes Gay-Lussac law. If the pressure is cell constant, it becomes charge law. If T is cell constant, it becomes Boyle's law. Therefore, all these 3 gaseous gas laws are included in combined gas law. Let's see which one represents the Gay-Lussac law. Gay-Lussac law is P1, P2, P1 divided by T1. Do you remember that? Which of the following laws relate to the relates pressure and temperature? Pressure and temperature. Volume is kept constant. That's Gay-Lussac law. Pressure and temperature. D is the correct answer. Boyle's law and Charles' law is combined. Therefore, this is a constant. After Avogadro's law, we came up with a constant is equal to n and came up with the equation PV. That's the ideal gas law. We're going to look into that later. So let's do a few more calculations. The gas occupies V1 and P1. Volume question. P2. That's Boyle's law. Boyle's law is when the temperature is held constant, same temperature. So you can drop this. This is held constant. Therefore, combined gas law reduces to Boyle's law. So we can solve for V2 here, rearrange the equation, and calculate the volume, new volume. Which of the following is the combined gas law? Sometimes you have to rearrange P1 V1 divided by T1. This is correct. Let me think about this. This is not correct. P1 V1 T2. That's not correct. P1 V1. That's correct. P1 this is incorrect. So is this. Answer is C. Suppose a balloon is filled with volume. When the pressure with a gas, pressure is P1, and the temperature is, what is the volume of balloon? When the temperature is, that's T1, T2. This is combined gas law. So you get the combined gas law equation and convert the temperatures to Kelvin. Add us 273 and plug in the values, temperature values. 300, 297. So rest came from P2 here. That's P2. T1. T2. You get 3 liters. Answer is T. Gas laws that relate. Gay-Lussac's combined gas law. After Gay-Lussac's law came, we combine all these three. This is Gay-Lussac's, same as this one. This is combined gas law, D. I am going to start on Avogadro's law and talk about how the amount of substance affect the volume of a gaseous sample. You guys there? Are you guys still there?
Yes, sir.
I'm going to stop the class for today. We're going to meet on Wednesday, coming Wednesday. All right. Please sign the
Yes.
chat box. I will see you on Wednesday. Okay.
Yes, sir.